Hello, these are the exam review slides for exam 4 from the fall 2021 semester. So in these 3 chapters that we're going to be going over in the for the exam, right? So this is all about carbonyl chemistry. And so first one, right? First chapter was about aldehydes and ketones and how you're going to be able to attack directly on that carbonyl and push those electrons up. Next chapter was dealing with carboxylic acid derivatives, where where again we're going to be attacking at the C of the C double bond O. Those electrons come up, but the electrons can then come back down, collapse down, because there is a leaving group on the C double bond O. With aldehydes and ketones, you're going to be only breaking. If you were to try to collapse it down, you'd only break carbon-carbon or carbon-hydrogen bonds. And so the O just has to stay as an O-, which then gets protonated in the workup to be an OH. For aldehydes, or for carboxylic acid derivatives, you're going to be attacking at again, C double bond O, but the O can collapse down because there's a group that can leave, something that's not a carbon, not a hydrogen. But there is a ranking on how reactive these molecules are. Okay? And so if you look at here, you're going to need to know this list. So the most reactive are the acid chlorides, then the anhydrides, thioester, ester, and amide. And then carboxylic acids are going to be here. For this list. Okay? So when you go from your starting material to your product, you can either stay at the same level or you can go down, but you cannot move up. So you can make an acid chloride to make an anhydride, thioester, ester, or amide. For a thioester, you can make an ester or an amide, but you cannot go from thioester back up to anhydride or acid chloride directly. Okay, so that's this list. Okay, and the reason why the reason why these are the list there are is because what gets kicked away, in this case it'd be a Cl, right? So Cl minus. Here it would be the carboxylate. Okay. Here it would be the thiolate. Right. Here it would be the right, it'd be the O minus here. Here it would be the NH2 minus. Right? As you go down this list, these groups are becoming more and more basic. Okay, so remember, we want to be able to go from a strong base to a weak base, right? So that, just like we want to go from a strong acid to a weak conjugate acid. Because remember, there's that duality of things that are good bases are generally going to be good nucleophiles. Okay, and so if we look at here of what leaves these groups, okay, we're kicking off very up here. These are very, very weak nucleophiles. These are strong. Okay, so these are more likely to leave. So that's how the list comes about. So when you look here, right, you're looking at the C double bond O, okay? And so for this one, here's a C double bond O, here's a good leaving group here. So that means this is our nucleophile, right? And so when you come in here, it's going to attack there, right? Because that's where the polar covalent bond is, right? Can't have 5 bonds, so you got to push those electrons up. When those collapse back down, it's going to kick away the leaving group, and as it goes away, the leaving group is going to grab this hydrogen as a souvenir. Okay? And so what you're going to be left with is this. There we go. And so what you're going to do, right, you're going to say, okay, here, this is a thioester. Right? Here, this is just a regular ester. So so we're going down that list. Okay? So we're good. So for here, right, so we have the, right, actually we have two C double bond doubles. But notice how this one has the negative charge on it. So that makes this one going to be the nucleophile. So it's going to attack here. Right? One of these lone pairs is going to come here, right? Up, down, kick away. And so you're going to end up with this. Right? And then Cl. And so here we're going from, right, we're going from the acid chloride. What you want to do is you want to look at the group that's getting attacked over here, and then your product, which in this case would be an anhydride. Right? And so that's okay. So reactions to know. Okay. So here again, these are just the reactions that we were talking about before, where you have say an amine comes in attacks, right? So you have a lone pair here, attacks, up, down, kick away, and so you're going to be able to go ahead and couple this, right? Because your amines at the bottom, so it doesn't matter as long as it's above it. Here again, that's how all these are. Now the quirky one is going to be when you have a carboxylic acid and an amine here. Now normally you would, if you're looking at the reactions, this should work just fine. But there's a quirk here that you have a carboxylic acid group here, which is acidic, and you have a amine group here, which is basic. And so if you just mix these two together, you're going to get a very nice acid-base reaction where this amine group just rips off that the carboxylic acid, and so you just get the salt. This becomes O minus, this becomes N plus, and you're done. In order to actually do the coupling, you have to add a compound called DCC. So what happens with this one is the DCC reacts with the OH, turns that into an ester, and then the nucleophilic attack can go as normal. Okay, so you have to have, if it's a carboxylic acid and an amine, you have to put DCC in there. Okay. Now, the other thing is, how do we make acid chlorides? Well, one of the reasons why they're called acid chlorides is because they're formed from carboxylic acids. Now, this one is thionyl chloride. Its sole purpose in life is to convert OHs into CLs. Whether it's a carboxylic acid or an alcohol, it turns those into CLs. Okay. And so that's what's happening here. So that's how we make the acid chloride. Is you start with the carboxylic acid version of it and then add the thionyl chloride. Okay. Now for these, right? So we have the Grignard reagent here. Now, if you have an ester, the carboxylic acid derivative here, what can happen is you can come in and attack, up, down, kick away, so you add one, but this ketone is still going to be reactive, and so you can get another nucleophile coming in that goes up here, which now you'd have to kick off a carbon group, which isn't going to happen, so you end up with the OH. Same thing happens with these guys, with lithium aluminum hydride or BH3. This is sometimes also NaBH4. Okay. Those can come in and do the exact same thing that's happening up here, it's just with hydride. Right? These are a source of H-. Now the other ones you need to know is for if you have an aldehyde or ketone and you mix it with a primary amine. Okay, so this is primary, right? Because there's only one non-carbon group on there, right? So if you draw it out like this, right? There's only the one non-carbon group on there. Okay? And so this is a primary amine. Okay, so that makes this primary. So that means when we make when these react, this nitrogen is going to replace that oxygen. But since it's having to sacrifice two hydrogens, that means those get replaced with carbon-carbon bonds. Okay, and so the oxygen and these two hydrogens form a water which squirts out. With a secondary amine, right? Now this one here, it's the reason why it's secondary is because now it has two non-hydrogens on it. Right? So here and here. So this is a secondary. So the nitrogen can only donate one hydrogen to the nitrogen, so it only gets one bond. The other one ends up coming from here. So from this carbon here, since it's donating hydrogen, it gets an extra bond to compensate, and so that's why you get the double bond here and the enamine, excuse me. Okay. So for lithium aluminum hydride, okay, so with that, this is a source of H-. So this can actually take things all the way down from esters all the way down to alcohols, because you go from no CH bonds to 2. Okay. Now for sodium borohydride, it can take and so this can go even with carboxylic acids, esters, and aldehydes can do this. Sodium borohydride, it can do the aldehydes and ketones, but it could also do but it's not powerful enough to do carboxylic acids or esters. Okay. So SWERN or PCC, this goes one step. So you convert one CH bond into a new CO bond. Okay, so if it's a primary, you're going to aldehyde. If it's a secondary, it's going to turn into a ketone. But with chromic acid and sodium permanganate, you're going to convert all of the CH bonds that are on this carbon up to new CH bonds, or CO bonds. Okay, so if it's a primary alcohol, you're going to end up with a carboxylic acid. If it's a secondary, it's going to be a ketone. Now for both of these, right, if it's a tertiary alcohol, okay, there are no CH bonds on that carbon where the alcohol is hanging off of, so those are resistant to it, okay, because there's no CH fuel to be able to oxidize. Okay. Now for down here to make carbon nucleophiles, right, we can take the bromide and mix it with either the lithium to make the organolithium here, or the Grignard here, something like that. So the reason why this is Li and this is MgBr is if you look at the charges, because this carbon here, right, it's essentially has a lone pair with a negative charge. The lithium is going to traditionally has a +1 charge, so that's balanced. So if we make this one have its negative charge, right, remember that magnesium, because it's an alkali earth, it typically has a +2. So that means that it needs to have the bromine around to be able to balance that second positive charge. So that's why it's MgBr, but then lithium. Okay. The other ones to do is either the Wolff-Kishner, which uses hydrazine in the presence of base, or Clemenson, which is zinc-mercury amalgam in the presence of acid. Okay, both of these work the same way in that they just convert that C double bond O to a CH2. So you just get rid of the carbonyl. Okay, so now for reacting on the alpha carbon, okay, so what we can do is remember that a CH bond next to a C double bond O is going to be very acidic, and so if you throw in something like LDA, you can come in here and you can remove those hydrogens, okay, and then that can turn into a nucleophile, which can then come in and do an attack. Okay, so if you have something like an alkyl bromide, it'll attack where that bromide is to kick away. It'd be a nice SN2 reaction. But you can also do this with a halide. Okay, so in this case we put a methyl group here. Here we put the halide. And so if you want to put in a chlorine atom, all right, so for that you can have Cl2. And so when this is a negative charge, after the LDA reacts with it, it'll attack here, kick away one of those, but it'll be left with the chloride here. With malenate, okay, so for that, or ethyl acetoacetate, which is just this, okay, this CH bond is between two C double bondos, so it's actually much easier to remove. So you can do something like sodium ethoxide. Okay, that it just does the same thing here, but because this is a lot more acidic, you can get away with ethoxide. So with that, but again, we're going to be putting a negative charge here, right? And then that's going to attack there, kick that away. Okay? With an aldol addition reaction, right? So again, you're going to be grabbing this right there, but then those lone pairs can come in and attack there, kick that up, and so now you're going to be making a new carbon-carbon bond. So this is the new carbon-carbon bond that's made. That's how all the aldol addition reactions work. So for design of synthesis, what you need to do is you need to be able to look at this molecule. So it's going to be like this, where I tell you where you need to start and where you need to end. Okay, so remember, along this process, we're going to be losing one of the ester bonds, okay, for decarboxylation. So let's say we're going to lose that. So what that means is we've got this carbon here, oxygen, oxygen, end up being this carbon, this oxygen here. Okay? So what do we need to add to this? Okay, well, we need to add this 2 carbon piece here and here, and then a 1 carbon piece here. Okay? So the way you put it together is exactly the same. Okay, we're gonna react this with sodium ethoxide. Right? We want to match this this base with whatever the ester is. So if we did a nucleophilic attack, you would just make the same product. Okay? And so that's going to be removing one of these, right? Moving one of these hydrogens, moving that there. And so you're going to end up with this. Right? And then if we want to put in the ethyl group here, right? So, so it wouldn't really matter which one you put in here. So then we're going to dump in, say, this 2 carbon bromide, okay, right? And then that's going to attack there, kick that away. Now we go through the same process, but now we're going to add the green 1 carbon piece. And so again, we're going to be adding sodium ethoxide. Right? So that's going to be grabbing that, push those up there. And now we're going to be adding a methyl bromide, right, which again is going to attack here. Push that away, and so you're going to end up with this. And so now you've got your carbon pieces together. Right, you got a 1 carbon piece and a 2 carbon piece. So now you go through the same process, and now you go through the final steps of the process. Okay, we're going to be adding a lot excess sodium hydroxide. Okay, now it's actually important that it's hydroxide, because what we want to do is we want to convert them into carboxylic acids. And so, right, these are going to come in here, right, up, down, kick away, right, as well as here, right, up, down, kick away. And so when you do that, you're going to end up with carboxylic acids on both sides, essentially. Okay, so you're going to end up with that. Now, when you add acid and heat, okay, one of these carboxylic acid groups is going to go away. It doesn't matter which one, so we're going to say that one goes away, and you're at that spot. So the process you get there is exactly the same. The biggest challenge is figuring out the carbon groups that you have to add onto here, figuring out where which one of these carbon groups come from the original malenate or ethyl acetoacetate, and then the additional carbon groups that need to get on. Okay. Good luck.